ahead and kick off. If more people trickle in, then great. Thank you for sticking around for a Friday afternoon for the last one of the week. I am going to be talking about the thrilling side of processing aerial LiDAR data. Another thing why they put an actual technical processing one on Friday afternoon, oh well, but yeah, thank you guys for joining me. As you know from, if you guys have sat through any of my prior ones, I love questions. Please ask. I love to talk about it, especially because this is the part that I've referenced in my other talks that is the most rapidly changing of any of these parts of the drone surveying world. Photogrammetry has been around long enough that it's pretty much stabilized. There's been a lot of agreement over the best ways to do it. The hardware side has really slowed down the pace of change that we see. But the LiDAR side is still very much on that upward trend, especially the processing side. These workflows are changing very, very, very rapidly. By now, you guys know about us. We do drone data processing for surveyors, been around for a while doing that. You know about me, I'm the lead photogrammetrist. I'm also spearheading a lot of our work into establishing, developing, and operating our LiDAR workflow procedures. As I mentioned earlier, we have had 3 talks. This is the 3rd one. If you do want to have a video copy of either this presentation as well as the slide decks for all 3 of them, go to aerotas.com/LSAW22 to get all of that. All right, so what are we going to talk about today? We can just jump right into it and get right into the meat of it. We're talking about specifically processing LiDAR data. That means we're not going to be talking about the hardware. We're not going to be talking about how LiDAR works or any of the fundamentals. This is going to be very much on the ground in the software, actually getting useful data out of it. If you want that hardware stuff, that's in one of the prior videos that you can have. Because as we've talked about, photogrammetry and LiDAR integration is what we think to be a very key part of being successful with LiDAR. We will be talking about photogrammetry a little bit as well. And then the actual LiDAR parts of the workflow, that's going to be creating and geo-referencing the point cloud, classifying the point cloud, rasterizing your LiDAR data into raster data, and then vectorization of the features. If you don't know exactly what all of that means, you will by the end of this talk. And once again, I always reiterate this. I know I'm a broken record for those of you that have sat through my other talks. It is all, to us, it is all about saving time and money. Part of the reason why I can give this talk is because we have blown a lot of our own time on the R&D efforts of this, of spending 40, 50 hours on manipulating the LiDAR data for a single project, which makes no sense at scale, but it's necessary to develop these workflows in the first place. So these workflows are developed over a lot of blood, toil, tears, and sweat. You've seen these, so I'll go through them quick. A drone program should get you better deliverables, increase your flexibility, save you time and money, and LiDAR should be the same thing. LiDAR is very expensive, but when used properly, it will get you much better data than you had before. And you do that by not making the mistakes that other people do. That means don't use the wrong tool for the job, don't overspend on crazy gear, don't spend too much time in the office, and don't treat this like a research project, because what you want is a survey. That is what we are talking about today. How to go from flying the LiDAR drone, push and go, the thing buzzes around and gives you 25 gigabytes of raw data into a survey, because there are quite a few steps that go in between here, or between flying a drone and getting to this, and that can take an awful lot of time. And we're going to try and cut that time down as much as possible. Okay, so jumping right into it, no more intro. Office processing workflow. There are 3 major steps to actually getting to that final survey deliverable after you have flown the drone. That is going to be 3D model processing, and what that means when we talk about it that way is going from the raw data to a rich 3D model. Rich 3D model is going to be your full resolution point cloud, your full resolution ortho photos. Those rich 3D models are incredibly detailed. They have all of the information, pretty much all of the raw information that you have. But they are not a useful survey, so you have to draft your line work. You have to go from a rich 3D model to a simplified vectorized 3D model, and then you need to put it into CAD and merge it with everything else. Those are kind of the 3 major steps. And we'll be breaking it down a lot more into other steps, because this is what a lot of people start with. They start with that nebulous cloud of you fly the drone and you get to a survey, but you guys know well enough that there are more steps in between. So, the workflow that it looks like in a little bit more detail, and now we're going to start getting into what some of the file types are as well. You start with your photos, ground control, and RTK, PPK data. In the case of LiDAR processing, it's actually going to have IMU data, a lot more GNSS data as well, some of the other just raw data files. goes through Lidar and Photogrammetry Processing. That's the first step, which gets you to these rich model deliverables that we've talked about. That's going to be your point clouds, multiple point clouds, Lidar and Photogrammetry, digital surface models and ortho photos. Draft that vectorized line work. That gets you typically DXF data, 3D points, topo points, polylines, break lines, utilities, all of that. Finish that into CAD, and that gets you into your typical DWG if you're working in an AutoCAD environment. Add in your site culture, all of your various layers, street names, symbols, that sort of thing, and that's your final deliverable. On the Lidar side specifically, when we talk about Lidar processing is kind of mostly getting to this part as well as a little bit of the Linework drafting on the Lidar data, but really going from raw data through to here is where this Lidar processing part is going to cover. That starts with obviously collecting the raw data. That's pretty simple. I'm not going to go too much into that because flying a drone is easy. You push go and it'll collect the raw data. Going through Lidar Pre-Processing. Lidar Pre-Processing is actually a very important step, and one that, if you haven't done it before, is easy to think is just automatic. Lidar Pre-Processing is the step of taking the raw data from the drone and turning it into a point cloud, into an LAS file. The drones themselves don't actually create LAS files. They don't create point clouds automatically. Because a Lidar sensor, what it does is it just measures the distance from the Lidar sensor to the ground. It does that a couple 100,000 times a second. But what you need to do is you need to add that to the GPS data, where the drone was when it took that distance, the angle that the Lidar sensor was, the angle of the gimbal, and you need to process that, and then you need to apply a coordinate system to it. Are you doing this in WGS84, NAD83, are you using ellipsoidal height, geoidal height, all of that, before you actually get to a point cloud. This step, as we'll go into a little bit, is typically proprietary for each individual drone. So DJI, if you're working with the DJI L1, it has to be done through DJI's Terra software to create those point clouds. Various micro drones use their own software as well. I think it's based in like Trimble Business Center or something, but basically it allows you to integrate other base station data and actually create that final, or create a point cloud at all. Before that, you can't do anything. Once you have your point cloud, you need to align and geo-reference it. The points clouds are typically very good, but oftentimes need a little bit of tender love and care to actually get them to align properly with your project. Geo-referencing them to the point clouds, or to your ground control points, aligning individual Swots, as well as troubleshooting for errors, which we'll go into in a little bit as well. Then you classify the point cloud. When the point cloud comes in, obviously, by default, it is just all points. Whether it's vegetation or road, no one knows. So classifying that into ground points, vegetated points, building points, power lines, power poles, whatever you need can be a very time-consuming process. And in fact, that's going to be, depending on your workflow, the most time-consuming part, and where a lot of people spend way more time than they ought to. There are a lot of automated features out there. We'll go over many of them, some of their pros and cons in just a minute. But the classifying the point cloud is probably the biggest time killer for a lot of people working in Lidar. And then even once you classify it, then you still have a 25 gigabyte point cloud or something, which is still something that nobody cares about. Not nobody, but most people don't care about the actual point cloud. What they care about are useful features. So you have to go from that full resolution point cloud, even once it's fully classified, if it's fully classified, which, as I will talk about, you don't have to do. But if it is fully classified, you still then have to extract your useful features. You have to turn those hundreds of millions of ground points into a tin surface. You have to turn those buildings into building footprints, roof drip lines, utilities when they're marked. A power pole, for example, or let's just pick a lamp post in a parking lot. In the point cloud, that would make up, in the point cloud, a single power pole or light pole might be 50,000 points. The Lidar scanner hits it 50,000 times. You do not need 50,000 records of a single power pole. You need one point, possibly with a symbol, to show the orientation of the power pole. Maybe it needs annotation for how high it is, maybe it doesn't. But either way, you sure as heck don't need 50,000. So modeling that, getting it into something useful that then you can actually send to a client that is useful, that's where extracting those useful features come in. And all of this is happening before CAD. There are different ways to get all of that done, but these last two steps are the real time killers. So generally speaking, These first steps are what get you your accuracy, right? Collecting the raw data, pre-processing it, and aligning it, that's how you get an accurate point cloud. And these two steps are how you get something useful out of it. That's really the Lidar office workflow processing in a nutshell. As I mentioned in one of the prior talks, there are two ways to do Lidar processing as well, because we do it with photogrammetry. The first, what I would recommend for people getting started off, is process this in a serial manner. Do all of your photogrammetry work first, and then do all of your Lidar data. Create your raw photogrammetry outputs, extract your photogrammetry features, then go into Lidar to create your Lidar point cloud, align your Lidar point cloud with the photogrammetry point cloud. Typically that's how it works. You start with photogrammetry and then you align your Lidar to it. And then you classify and extract the Lidar features where you don't have good photogrammetry data, and then you can bring all of that into CAD for your final delivery. Yeah?
I'm intrigued. You do your photogrammetric analysis, then when you're saying you've extracted the photogrammetric features at that point, then you've done all the scout work of cleaning up your cloud at that point. You've said, okay, this is garbage, this is good, or do you have tools that you recommend where you can bring both of those clouds into the same environment and they can differentiate the good from the garbage?
Great question. Short answer is we don't actually do very much photogrammetry work on the photogrammetric point cloud. We do a lot more on the orthophoto and on the DEM and only a little bit in the point cloud. So what tools do we use to actually extract that? I think I have a slide on that later, but with photogrammetry, for example, anything that is going to be ultimately a 2D feature, we are going to want to extract that from the orthophoto by itself. Typically, that's going to be a much better way to get those 2D features out. And then we can bring, once you get those into a DXF format, you can usually port it across different softwares, whether you're using it in a specific LiDAR-specific software or a GIS software or even a CAD environment. We really like DXF as a intermediate output. That's a very common intermediate output for us, just because it's very compatible across different softwares and different formats. Does that kind of answer your question?
Yeah, I'm just trying to say, yeah.
Yeah, because there is one workflow that is very possible, and we do actually occasionally use, on more challenging projects, is to bring both the Lidar point cloud and the photogrammetry point cloud into the same point cloud processing software. And actually, I think many of my slides in here, and we'll get to it, have screenshots of both Lidar and photogrammetry together. And that's how we do it. We take the point clouds and put them both into a single point cloud processing software. So you can extract all of your data from point clouds in a point cloud processing software. The challenge with that is it's time consuming for the reasons I was just mentioning, right? Those 2D features, you can get those out of a point cloud. That's kind of a pain in the butt. So you can use a software like a global mapper. We like global mapper. It's a very compatible format. You can put orthophotos, surface models, tin surfaces. You can throw basically anything at it and it'll be able to open it up. But switching back and forth regularly between getting it from the orthophoto, getting it from the point cloud, creating grid surface models and elevation models, trying to draw break lines in 3D, it's just time consuming. That's the only reason we don't do it like that regularly, is not because you can't, but because it takes more time. So yes, we do often blend the two together. In fact, the workflow that we use most often is this one. This is how we actually draft most of our Lidar data. And the key step here is going to be at the top, is having procedures for splitting Lidar and photogrammetry extraction data. And this takes a good amount of communication, procedures, and teamwork as well. So for our procedures, what we have is basically a book of rules to describe when is the vegetation so much that we will get it from Lidar versus when will we get it from photogrammetry, such that the Lidar team is able to look at a project site and say, yep, here are going to be the vegetated areas that we need to extract and get clean Lidar surface data out of it. And the photogrammetry team will look at the photogrammetry model and say, those areas are too highly vegetated, I'm going to ignore them and only draft the hardscape data. And where we actually bring it all back together is not at the point cloud level, which is what you were asking about. We don't merge the data together in the point cloud level. We merge it later. We merge it at the CAD level. We found that to be a more a more efficient use of time. And again, not because you can't, but because that's going to be a faster workflow, we generally think. Does that kind of make sense for how it works? Yeah. So that's why we like it. We process our LiDAR data with Lidar processing tools. I should point out, part of the reason we only do vegetated data with LiDAR is not just because photogrammetry is more accurate, but this LiDAR data is a pain in the butt to work with. It takes a lot of time. I argue it takes more time to process LiDAR data than it does for a comparable data set in photogrammetry. And maybe that's just because we've been doing photogrammetry so long that we've got that workflow just rock solid. And LiDAR, we still have a little bit more room to improve it, to improve our policies, our training, and all of that. But right now, LiDAR, and just working in the full resolution point cloud, that is a time-consuming method of extracting data. So to go over just kind of those major steps again, so that we all are sharing the same kind of high-level workflow. You start with photogrammetry, get your point cloud orthophoto and digital surface model from that. Next step is going to be your LiDAR processing, where you classify that, create your digital elevation model so that you can convert it into useful formats there. Then you bring both of those rich formats into actual Linework drafting, where you extract your topo points and polylines and that sort of thing. And then you bring them together in CAD. That's what our workflow looks like. So again, I think I showed you this. LiDAR processing, rich models, Linework drafting, clean, simple data, CAD finishing into your final deliverable. This is a pretty important set of the workflow of how we actually get it. And the other thing that's important to us is having these clear distinctions, right? So once something is through this step, it's basically frozen, unless we discover any sort of very unusual accuracy error, if the client sent us wrong ground control point data or something. It's pretty much frozen. And then once we go through the Linework drafting, we try and freeze it here, and only if we discover did we miss something will we go back and have to draft some more data to bring it in and create a TIN model. Having these discrete steps and these discrete workflow, that's all going to be part of actually that reliable, repeatable workflow. All right, so let's talk about photogrammetry, just because this is an important part when blending photogrammetry and LiDAR data, and I won't spend too much time on this as well. Photogrammetry is, of course, the art and science of making measurements from photographs. So you actually can, these are some images from Pix4D, turn photos into your ortho photos and digital surface models like you have there. The big challenge with photogrammetry is it takes a lot of time. A little bit of human time, but a lot of computer processing time. That's one of the biggest bottlenecks for photogrammetry. You get larger sites, even with extremely powerful workstations, it can take 24 hours to run a photogrammetry process, and it just makes it run overnight. So obviously you don't want to get it wrong, or else you're losing a day with every mistake you make. So photogrammetry does take quite a lot of time, and improved hardware only does so much. If something takes 24 hours, you buy the most cutting edge computer, maybe you can cut it down to 20 hours, but if it's still overnight, that's not going to be a game-changingly different level of time. There are a couple of ways that you can process your photogrammetry. There's a lot of automated cloud-based processing tools out there, things like Drone Deploy if you're familiar. They're very good for what they are for doing cheap automated processing. We find they typically aren't accurate or reliable enough for survey grade work. But if you're just looking for a quick map, maybe an orthophoto backing that doesn't have to have 10th foot accuracy, your automated point cloud or cloud-based processing is great. Local software processing, that would be buying a computer, buying a Pix4D license, doing it yourself. Highly customizable, have the most control, but it is expensive buying all the software and hardware, a long learning curve, and takes a lot of time to do it. Or hire an outsourced photogrammetrist like myself or Aerotos, where we actually have all of those things and we can process your data for you. But really, any of these work. You just got to know what your needs are and what you want to do. Our principles for photogrammetry is a little bit different for LiDAR because it has that weird nature of being so computer time intensive. We have an iterative process for photogrammetry processing, where when we start processing, we process every project typically at least 4 or 5 times using slightly different settings as we recalibrate the camera to try and figure out the exact optimum camera calibration parameters and other settings to make sure that we get the highest accuracy possible. Processing that into sparse point clouds, integrating control points, reprocessing it, running QA/QC, running our check clouds, before creating dense point clouds and then running more and more QA/QC. And that is because a lot of every project is going to be unique, whether it was flown with changing lighting conditions over multiple days, the accuracy of the drone, heck, even the weather can impact the exact camera calibration parameters. If the temperature changes too much, the slight change in the camera lens is enough that we can actually detect that on a photogrammetry level. And also, we do a lot of parallel processing with photogrammetry, particularly for larger sites. We like to break them up. I mentioned that in the Lidar photogrammetry that we like parallel processing. That really helps make things efficient in terms of time. So you could have one person with one computer and it might take them 3 or 4 weeks to do a very large project by themselves in a linear manner. Or if you can create good procedures to split that up over multiple computers, multiple teams, multiple drafters, you can go a heck of a lot faster with very, very large projects. We are really big believers in parallel processing. People very regularly ask us what our hardware stack is, and that we will happily share because it's not really magic. For anyone that's familiar, these are what would be a very, very high-end gaming computer, but not a enterprise level fancy server or something like that. These run about $4,000 to $5,000 a piece, whereas your actual server grade stuff can often be 20 grand or something like that. But using photogrammetry software correctly is much more about, it's not about the settings. There's no magic set of settings that just makes everything work properly. It's about getting the right workflow, like a lot of this stuff. Having that standard workflow in advance. Yeah, question?
Just a random question on your system specs. Do you find that Pix4D works more efficiently on the cards that are kind of built more for gaming as opposed to the ones that are built more for processing, like a quad or something?
Great question, and the answer is Pix4D is generally not going to be GPU bound. It is going to be CPU bound, that the actual CPU processor is going to be the biggest difference. And that's where the Ryzen 5950s are going to be some of your most powerful CPUs. The GPUs help, but they're not going to be a major difference on there. We have some servers that run NVIDIA, some that run AMD's type stuff. We've never really bought into any of the Quadro stuff just because in our experience, it really is not the bottleneck at all. Yeah. As far as where, if you're gonna spend an extra couple $100 on something, actually getting a much better hard drive winds up being a bigger difference maker than that last inch of performance out of a GPU or something. Even the 3090s, if you're familiar, are probably overkill for a lot of these things. The other thing that I'd say when it comes to the cost, part of the benefits of parallel processing is if you double the cost of this machine, you might be able to improve processing and actual performance by 20%. Or you could buy 2 of them and run them in parallel, and then you've actually doubled your processing throughput capacity. So that's what some of our kind of philosophies are behind hardware. And then the Lidar processing computers, I've got another slide on later because that's actually a different set of bottlenecks that can help it out. But with photogrammetry, as much as that's a really nice computer, you can run it on way slower computers. We actually still operate some of our servers, our photogrammetry servers that are 3 or even 4 years old because we can still make good use of them as long as the workflow and procedures are actually working out correctly. You do want to manage processing time with all of these things. I talked about it in other sessions, but a lot of your processing time is really determined in the field, not once you're actually processing. Having good flight operations is really critical to actually reducing the amount of processing time that you have. And like I said before, a good workflow is worth much more than a good computer. A lot of people wish that they could go out and just spend $5 grand on a new computer, on new processing chips, and that would actually solve all of their problems. That's not the way that it works. So typically a good workflow is going to make a heck of a lot bigger difference than new computers. And also, if you're interested, you can check out the American Society for Photogrammetry and Remote Sensing. I am certified by them, and they do these certifications for actual photogrammetrists. They're a nonprofit organization. We are not affiliated with them in any way, but we just think they do good things for the community in terms of education and getting all that set up. All right, so now we can get into the details of the actual Lidar processing. So you've seen this kind of slide before. You start with these 5 steps: raw data, pre-processing, align the geo-reference, classifying your point cloud, and then extracting your features. And it's from there that you go into those final steps that would be getting it into CAD, merging it with photogrammetry data, and creating those final deliverables. So let's start with step one. Well, actually, step one was create raw data, and that's simple. Push go on the autopilot. Okay, you've collected your raw data. Now let's get into step two, I guess, which would be Lidar Pre-Processing. So what this does, and I mentioned this earlier, you go from raw proprietary data to a clean, useful point cloud format. Your point cloud format is typically going to be LAS for the laser scanner file, LAZ, which is a zipped format, but there are dozens of different formats point clouds can be saved in. LAS and LAZ are just going to be the most common. XYZ or text files, or there are a whole bunch out there. The exact steps and software is different for each hardware stack. One of these, like a Lidar USA one or a Regal sensor or a Velodyne sensor, they typically have their own Lidar integrator software to turn it from their proprietary data formats into an LAS file. This is what some of the raw data looks like from a drone. If you're familiar with any of these, you have some raw IMU data, some RTK level data, you have some satellite observations, both from the drone as well as from the base station. You have your actual laser scanner data itself, and this pre-processing step actually blends it all in a proprietary software into that final point cloud. The reason this is an important step is that typically you don't have to worry about it unless something goes wrong in this, and that's when you kind of have to start looking at it. A lot of these softwares just have glitches in them. That's what software does. Sometimes there might have been a glitch recording the GPS base station data, and you need to sub out your local base station for a network corrected base station RINEX data or something like that. It's fairly uncommon, but it is an important step, and it can be a source of error down the line, especially when a lot of these softwares they're pretty black boxy in that you put data in, you process it, and it gives you data out. They don't tell you too much about exactly what solutions they're running. So not a lot in terms of tips for that, but it's important to know that this is a critical step to getting accuracy, and what comes out of it is then going to be your actual point cloud. Make sense? Any questions on that stuff? Cool. One of the next steps is going to actually be aligning your Swots, and this is a step that is dependent a little bit on exactly how you did your pre-processing step or your GPS base station data. But different flights, or sometimes different swaths within the same flight, once you start processing it, what you will wind up seeing is that they don't exactly align quite the same with each other. That these two, this was one flight, and then I think they changed base station, went to a different takeoff location, flew it again, and it just didn't line up right. This was like a foot higher here and a little bit lower here. This actually happens quite a bit with Lidar, as the data can get ever so slightly shifted. So you got to make sure that you align those swaths. Sometimes you have to shift one a little bit further north, a little south, a little east, west, up, down, just to get everything to align properly into a single cohesive point cloud. This is where having check data can really help, because especially we haven't integrated any ground controller check data yet on this, but check data can help because it can tell you which one is actually accurate versus the other ones. The individual point clouds, as long as you follow the procedures and there's not an error in the hardware, each individual point cloud is going to be precise by itself. Precise meaning that any 2 points on that one point cloud are very good, but they're very often not accurate, which means that that point cloud is not accurate within the world perfectly. It might need to be shifted by sometimes as little as a few tenths, sometimes nothing at all, and sometimes as much as a couple of feet. But that's very common to be able to shift these in some sort of Lidar processing software. There's some software out there that is designed explicitly to do this. I think there's one called TerraMatch that only aligns point clouds with one another. That's all it does. Or you can do it in a software like a Global Mapper, a TerraScanner, an ArcGIS LiDAR unit, or something like that. As far as geo-referencing the point cloud goes, we really like ground control points. I've said that a bunch in all of my talks. If for no other reason than it lets you localize it to your existing project. And one of the ways that you can actually do that is not just by using ground control points, which can be hard to see, especially in your X and Y, but you can actually compare a photogrammetry point cloud to it. You're asking about blending the data. Sometimes you can throw the 2 point clouds in together.
Now, I'm assuming you're about to cover what you're about to cover, so I'll try to shut up, but I have a really hard time shutting up.
That's all right.
You've
I
got
like
these
it.
3 or 4 or 5 or 6 clouds that are discontinuous from each other, and they've got obviously biased one way, biased another. And you said, you kind of waved your hands over it, says there's software that sorts that shit out. And I'm kind of going, yeah, but how does it decide which one is right? And I assume you're using GCPs for that, or are you?
Great question. It doesn't, and that's the part. So when it shifts into a when you're at this step, it doesn't pick one that is the absolute correct one at this step. It's still, at this point, you're not looking for accuracy yet, you're looking for precision. You're getting all of these to line up so that they are internally consistent with one another, and then once you have that single block that you know is precise, then you bring that whole block to your ground control points to make it accurate. So, and you can run, we run a lot of, like I said before, we have an iterative process with this. We import our GCP data early into this process to check it, so that when we have this step, we actually will typically run a quick QA check against our GCPs right here as we're aligning the Swots to see, okay, which one is right, which one isn't. So if we do have good GCP coverage, which you should, then you should be able to align them and have the control points integrated at the same time.
Okay.
Does that help you out a little bit? Yeah.
He's just eating at me, that's all, dude.
Follow-up question to what he was saying. So the proprietary software that comes with the LiDAR units does not cover overlap corrections. It only just gives you that, basically?
Yeah, typically not. And again, this depends on how you do it, how your base station is set up, how you're streaming corrections, whether you're localized, whether you have your base station set up over a known point that already has an Opus solution that you've already calculated, or whether you need to post-process the location of that base station and shift it after the fact. That's a tricky one that honestly goes a little bit beyond the scope of this talk in terms of the detail of exactly how you can run the GPS processing workflows, because that's a very complex set of different options, of which, like a lot of these things, there is no exact right solution. I said before in some of my other talks, our preference is always real-time kinematic GPS data with a local base station, and then we can run any corrections that we want in post, but there are other ways to do it. You can use your network-based corrections, which if your network corrections are working properly, you shouldn't be seeing anything like this on your GPS data, but sometimes you do because your actual if you have longer baseline distances and your tropospheric correction or errors are consistent in one direction from one day to the next, you still actually can see this type of thing when you are doing network-based corrections with longer baseline distances.
So does the M300 L1 package come with the local base station?
It does, yep. It comes with DJI's DRTK2 base station, which is very good at one thing and one thing only, which is streaming corrections to DJI drones. They try and put other stuff on their website like, oh, you can use it as a handheld surveyor. Don't. The software for that is terrible. I don't trust their leveling bubbles. I don't trust that the phase center of their antenna is perfect. But it is super duper great and reliable for streaming corrections so that the M300's LiDAR system is extremely precise. And that's part of it. Seeing this sort of data when you have that DRTK2 base station is quite common, especially, well, it's most common when you move the base station, right? You take off, you fly from a different part of the site, it'll relocalize that base station and it'll localize it perfectly so you have that offset. That's very, very common.
Do existing Phantom 4 Pros have receivers for the RTK data, or is it a specific Phantom 4 that is able to receive those corrections?
It is a specific version called the Phantom 4 RTK. Okay. You can tell because it has a little cylinder on top that is their dual band. So if you have your standard Phantom 4 Pro, it cannot receive GPS corrections. You need specifically the RTK version.
And sorry, one more follow-up question.
Sure.
Processing this, is it similar workflow to just manually combining two terrestrial scan stations, which kind of pick your light points and?
Yep, pretty similar. There are a lot of different statistical ways to do it. Sometimes you pick light points. I really like using houses. This is a great example because you can actually see a lot of these points that need to be aligned pretty precisely. This right here actually is an example of a photogrammetry point cloud and a Lidar point cloud. Oftentimes you can tell when it's one and the other because The Lidar point cloud is going to be in some solid color like orange, and the photogrammetry one will be actually real world colorized because it's derived from photos. But that's one where you can actually get this to be shifted, you know, maybe it's a little left, a little north, and a little down or something like that. But finding those points and actually aligning them by picking known points, that's one way to do it. Finding features and drawing the perimeter of a house so you can tell exactly where to shift it. I always like doing my X and Y shifts first and my Z shifts last. So finding those identifiable points in 3D to get those XY shifts is a little bit tricky and requires a little bit of time and error, but that's my favorite workflow for shifting those together. There are also some ways to do it by, this is a more advanced one that we use to align Swots, is with that DRTK2 base station, what you can do with the L1 is after you fly it, we run an Opus solution on each individual base station occupation. It's sitting there for, you know, an hour or two, so you have plenty of data to run a good rapid static solution on it. And what we do is we can calculate, okay, what was the initialized location of that base station, and then what is the Opus solution location of that base station, what's the difference between those two, and that's typically what we have to shift those point clouds at. So we can actually get, oftentimes, a swath alignment number prior to even looking at these. And then we apply those numbers that we use on PPK processing to the point clouds, and then just run QA/QC from there to make sure it all aligns. And that's proven to be a pretty darn reliable workflow so far.
Do you ever reinforce your Opus solutions with, your local GPS, your survey grade GPS? Because you're probably you do a base station setup and your flight Opus rapid statics 15 minutes. So, and that's not a great solution.
Yeah, so absolutely yes.
Okay.
We do all of that to get all of that is still, we're just talking about getting that single precise point cloud, not your final point cloud. Because your final point cloud, you want it localized to the site. So we will always trust ground control over our Opus solution. And the other thing, I say Opus solution, it's a little more nuanced. Opus doesn't actually support the DRTK2, so we do run PPK processing across multiple cores baselines to actually try and get a single fixed location. It's a little bit technical if you know your GPS stuff too well, but it's not technically an Opus solution, it's just a very similar process. But what we always like to do is localize with control at the very end, because that really helps you get everything on a site together. Even with Opus, you might have some systematic errors that everything's half a foot too high. And if you have your control, you just shift it down. It's just easy to make sure that everything is perfect to the site. That's what we always rely on, is control over everything else. So control is very important. We've said that before. We like our ground control points. Not only that, man, they are simple, reliable, cheap, verifiable, and they're so good at just spotting blunders. There's so many easy ways to make stupid mistakes that really can ruin a project, and just having a couple ground control points makes it very, very good to do. Likewise, part of the reason we talk about that, a lot of LiDAR hardware relies on GNSS and IMU processing alone. We have talked a lot about it, and GPS is very, very good, but it is not perfect, and it's not good at checking itself. Especially because the drone is flying, you can't reoccupy a point. You can't measure a point once at the beginning of the day, and then again at the end of the day, just to verify that your systems are all still working and that you don't have systematic drift over the course of the day. That drone is moving at 30 feet per second, and it is not stopping, and you can't go back and measure the same point. So that's part of why I really don't like a lot of the hardware people that say you can operate drone hardware without any ground control points, because if nothing else, you just want to verify that something didn't go wrong, because sometimes things go wrong. So yeah, there are ways to geo-reference it. Blending it with photogrammetry workflow is really great. Comparing LiDAR to photogrammetry, using those colorized point clouds when they are available to find that XY location, shifting it there, all of that is very, very good to geo-reference your point clouds. Once you have a geo-referenced point cloud, there is an interesting question that is one of those parts of drone surveying of the LiDAR processing debate that's still very much open for discussion, is whether or not to thin your point clouds. These systems create massive amounts of data. We've had projects that have well in excess of 1 billion LiDAR points in a single project. That will bog down even the most powerful computers, even with very, very good software. So there's the question of, do you actually thin your point cloud once you do it? Well, we're not entirely sure what the right answer to that is going to be. Thinning your point cloud, there are a number of different methodologies you can actually use to thin it. You can just do what we often call a dumb decimation process, where you just take 9 out of every 10 points and throw them away. Now your point cloud is 1/10 the size it was, and it's a nice statistically even average sampling of those points. Well, that's good, but you might lose what might be a couple critical points where you actually only do have a couple of returns from the laser on a single top of a power pole or something. If you're doing power lines where you are measuring small features that might only have a couple of points, that's not a great way to do it. There are 3D thinning algorithms where if you do have a point that's pretty much by itself, it'll keep it, and then if you have points that are in clusters, it'll combine those into one point. Well, that's actually a really clever way to do it, but it's not a statistically average distribution, and you might have way more density in a trunk, and especially when you're dealing with grasses, it might make grasses look more like asphalt because it's combining all of those into the same density of points as actual asphalt. So it's not great when you're dealing with partial vegetation. You can see how this ground surface here, this was done with a 3D thinning algorithm. This ground surface went from very, very dense cover to just a few. So it's actually introducing some noise into the ground, whereas the tree kept most of its points through a lot of it, which isn't exactly what you want. So there are some challenges associated to it, and all of this is in the spirit of trying to make the data more usable, actually. So generally speaking, we like to avoid thinning if at all possible, just to work with the richest data out there. But sometimes we do have to thin a little bit just to make the data more usable. Some point clouds are ridiculously dense. With these drone LiDAR systems, you can get 50,000 points per meter density or something like that. It's just crazy density that you can get. So we don't love thinning if we can avoid it, but if done right, it can make the file sizes much smaller and make it work a lot easier. Other methodologies you can use instead of thinning is just straight tiling. A lot of people will tile their point clouds, break them up into smaller chunks and process them one at a time. That has its own trade-offs too. It creates a lot more overhead and work. You have to work on this tile and then close it, reopen the next one, work on it separately, and then at some point maybe open them both up to make sure that all of your work aligns properly at the seams and everything. So tiling is another option for dealing with very, very large file sizes. But this is one of those questions where I would expect, if I were to give a talk like this next year, that I'd have some more clean recommendations of, okay, we've tried these different ones, this is what works out best for us, these are the best methodologies for thinning, and these are the ones to avoid. And then, once we're still here, we're still working in the raw point cloud, we haven't even gotten to the classification or vectorization yet. Running QA/QC checks. LiDAR data, like all data, is subject to a certain amount of noise. Some is idiosyncratic and some is systemic. There can be gaps in the data, and one of the things that we've started to see on a lot of different LiDAR systems is having systematic error at high scan angles. This is an interesting picture that I've done. So at the top, this is looking top down, and the points are colorized by scan angle. So that means these blue points in the middle, that's looking straight down along the path of the drone where the LiDAR sensor was pointing straight down. And the colors turn from green to yellow to red as that LiDAR scan angle goes up, a higher scan angle. Higher scan angle is going to mean that the laser itself is actually going quite a bit further from the drone. It has longer distances to travel, and it has considerably more noise in it. And what we see on a profile view from some of this is that some of these red ones, the high scan angles, are showing some systemic differences from the medium and low scan angle ones. Yeah.
So how are the individual point clouds being separated and shown? So like the drone runs its lines, is it taking a continuous line, or can you splice it yourself, or is it automatically splicing it for you?
Depends on the system, and that's part of the pre-processing step. So for the DJI-L1, the individual LAS file blocks are going to be based on each flight, effectively every time you change the battery. So it'll be one block might have 4, 5, or 6 flight lines. Some of the other systems that we've seen have every single flight line in its own block, so you can adjust those independently if you need to, or something like that. Typically, if you're using the local base station, having each individual flight as its own block is sufficient. You don't need to make other changes. When we see things like this, though, this is within the same flight. This might be, 2 minutes after when this point was taken from when this point was taken. What this is a sign is a little bit of just noisy data. It's part of why we actually like having higher overlap than the minimum required in LiDAR data, so that in something like this, we would typically exclude much of that high scan angle data when we are seeing these types of noises, or this type of noise, which winds up getting us a much more consistent point cloud altogether, and gets you final overall accuracy, or better overall accuracy. And I should point out, these differences are fairly exaggerated. This was an example used because it was particularly bad. Really, even if you don't process this, if you don't fix for stuff like this, it'll be adding a couple tenths of a foot of error, but it's not like you're gonna be off by 2 or 3 feet or something like this. When it is taking the statistical average of all these points to create a surface, it's not gonna create crazy errors, but we care about getting that last, 1 or 2 tenths of a foot of error.
This is kind of intriguing. I come to this whole thing from the world of hydrographic surveying, and we have patch tests that we run on any multi-beam swath we run, and the errors are exactly what you're showing there. But we have certain protocols in place before we start surveying to cancel that out and nullify that by running in different directions and at different speeds and that sort of thing. And then we get our roll and our biases negated that way. Is there anything like that in the system, or is it all as a post-process? Is there anything that the machine does that's the equivalent to a patch test like that?
Great question, and short answer is we're working on it.
Okay.
That's the type of thing where I'd like to get better at. How do you run a test on the hardware? How do you analyze this before it happens? Some of this can likely be solved by an actual proper calibration of the LiDAR sensor itself. It's a little bit tricky because that requires a very close communication between the people that are operating the hardware and the people that are processing all of the data as well. And we are very much looking into that to try and negate this. Are there flight patterns and flight parameters aside from just slightly higher overlap that we can use to get much more reliable patterns or much more reliable data based on the flight operations side? Right? I said with photogrammetry, flight operations is so big, that's where most errors come from. There's probably a flight ops solution to this that we just haven't figured out yet what the perfect one is.
Do you think theoretically this one wouldn't necessarily need patch tests because it's an integrated system, so those offsets never change?
It's intrinsic to the measurement that you're taking, though. I mean, you can't segregate it. I mean, you can say the same thing about your boat with your IMUs and your GPS. It's all taken care of, but in fact, there's always going to be biases because you're working in the real world. Yeah. And that's why you have to go salinity changes, temperature changes, all those things still apply. I'm just saying,
no,
it's the kind of thing where it's like, if you had a run, and never mind, is the answer now, but it could be part of a future integrated package where you had an 8-minute session where it said, okay, in these conditions, we've run these patch tests, we've determined these biases, and then you have a scientific approach to that site. It has to be worth doing.
It's a great question, and it's part of the LiDAR side that actually excites me. Like I said, this type of thing is still very much in flux. What are the right ways to do this? And part of it is that balance too. I don't want to send you guys out in the field and say, all right, before you can do anything, you have to do an hour worth of testing flights. And then you need to send us the data, we'll validate it, and then you can do your real flight. That's a terrible field workflow, right? So we're trying to create that right balance between what's a good field workflow, what's a good office workflow. If we can get rid of this in post and handle it only in post, boy, that saves a lot of time in the field, especially if we can make that post-processing smooth and easy. So what's the right balance? I don't know yet. We're figuring out exactly what that Goldilocks zone is.
You can post-process your patch test, though. So, I mean, it could just be part of its flight profile.
Yep. Moving on from that, though, a lot of this is all about accuracy, right? One of the important things when we're talking about accuracy and even about these tests is always make sure you verify it. we're very good at processing all this stuff. I like to think I know a good chunk about actually processing LiDAR and photogrammetry data, but ultimately I always say, don't trust me. Trust the data, verify the data yourself. One of the best ways with all of these different systems and with all of the different analyses that you could perform on it, what really matters at the end of the day is what's your final accuracy. And running what our kind of accuracy gold standard is the ASPRS Positional Accuracy Standards for Digital Geospatial Data, last updated in 2014. If you are a digital masochist like myself, that is 20-something pages of extremely academic analysis and standards for actually measuring and validating accuracy data. It was published to be sensor and methodology agnostic, so it actually has a lot of LiDAR systems in there, even though it was from 2014, that is very, very good at basically how to scientifically and rigorously validate the accuracy of your final product. And this happens at the end stage, right? Once you're done with all of this LiDAR point cloud processing, it basically tells you how good did you do after all of this stuff, after all of these tests, after all of your scan angle things. And that way, one of the things that I look at is, okay, once we're at the end of it, is it good enough? Is it within tolerance, right? I don't ask the question, can we make it better, always. There are two ways to look at it, right? There's your R&D mode. When you're in research and development, I ask the question, can we make it better? How do we make it better? But in production mode, when you're actually trying to get a job done, I ask, is it good enough? Those are very different philosophies, because can we make it better is an open-ended question that you can spend a lot of time making it a lot better. But when you're actually on a live job site and there's a client with a deliverable and a due date, you want to know, is it good enough for that, and can we deliver it on time and on budget? So research and development, that's where you blow all your money and time. Production, that's where you need to know, is it good enough? So that kind of is one of the other sides of things. There's the research side of me that loves asking the question, how do we make this better? What can we do to make this better? And then there's the production side of me that says, stop asking that question. It's good enough. You are wasting time. So it really kind of depends on that. And that's part of why I probably struggle too with what you're saying. Well, you could do this and this and this. Those are R&D questions. And when I'm in R&D mode, I love it. And then when I'm actually in conferences like this, remember what I said at the beginning? If it's not saving time and money, it's not working. You can't live and run a business in research and development mode because you won't save time, you won't save money at all. And then your boss is going to pull your budget, fire you, and send some kid out into the field and pay him $12 an hour to shoot it manually. And that's not a good result to all of this either. So that's where I very much get conflicted with the research and the can you make it better versus everything else. So for a lot of this stuff though, verifying your accuracy is going to be very important. Okay, let's assume, just for the sake of time, because I don't want to hold everyone up from the happy hour too long, let's now just assume that we have an absolute perfect georeference located accurate point cloud. Great, we did it guys, we got our perfect point cloud. It's still just a point cloud and we need to start with point cloud classification. So, there is a mix of semi-automated and manual classification routines that can be used. This is another one of those fields that is very, very rapidly advancing with lots of refinement likely to be seen over the coming years. Of classifying things into things like ground, vegetation, poles, power lines, as well as objects, structures, snow, railways, noise and artifacts. There is a limitless number of things that you could classify this as. I think it is really important to ask very early on, what classes do you actually need? Because classifying every single point in a point cloud is a very, very tedious process. Do you need to classify the difference between high vegetation and call that high vegetation, and low vegetation and call that grasses, and medium vegetation for shrubs? Do your buildings actually need to be classified as buildings? Because the answer is, for most surveys, usually not. You need to know about ground, but very often, unless you're actually doing a power line transmission survey, you don't need to know that that's a power pole. You just need to know that it's not ground. And the power pole there, you can maybe put one point on the power pole and extract that as a point, but you don't have to classify the entire pole. That's a very time-consuming, very, very time-consuming process. There are some situations where there are softwares that do need classifications, but even then, typically it's like, okay, we need these 6 classes because we're measuring the distance from the transmission line to other structures. So we need to know vegetation, structures, and ground. And those are the only points that we need. Cool, then only classify those. Don't waste your time on all of the other things. This is a big one that is a huge time killer. In here you see that we have trees and structures classified differently, but typically you don't need that. Especially if you're doing a topo survey, you are going to be ignoring those altogether. You're throwing them out. Maybe you'll take a couple elevation shots on a roof, depending on if you need that. If you need that, take a couple elevation shots, and if you don't, then throw it out. You really need to ask yourself first, what classes do you need, and only classify that. As far as the software goes, these are many of the different point cloud classification softwares out there. They all work, and as I said before, none of them is the magic bullet. I don't have an answer, and there isn't just some magical automated routine that, ta-da, it just makes every single point cloud classified properly. I'll walk through and I have a slide in just a couple of seconds that shows exactly why that is a near impossible goal. I did talk about computer hardware. You were asking about computer hardware for LiDAR systems. Generally speaking, LiDAR is not going to be computer bound. It is going to be workflow bound. More expensive computers do not solve many of the challenges with LiDAR. As with photogrammetry, a more efficient workflow is much more valuable than buying a new computer. That said, RAM is going to be important. Having at least 64 gigs of RAM, particularly for large projects. Having a high-speed hard drive, again, is there. Depending on the software you're using, a lot of the LiDAR softwares are actually bound by single-threaded CPU performance as opposed to multi-threaded CPU performance. If you're a computer geek, that means your actual Intel i9 processors are going to be the most powerful. And like before, your GPU is actually rarely the processing bottleneck just due to the computer architecture here. So again, 64 gigs of RAM and your high-speed hard drive is going to be important, but a good workflow can run on nearly any computer. With photogrammetry, just so you guys are aware of like how we think of it, photogrammetry, we run exclusively on high-powered desktops. For our LiDAR processing and our LiDAR techs, we use gaming laptops. They're laptops. They're not nearly as powerful as our desktops because that's not really the bottleneck like it is in photogrammetry. Photogrammetry is much, much, much harder on computers than LiDAR. Buying really high-end computers isn't really going to fix major LiDAR problems. All right, so let's talk a little bit more about classifying. Classifying ground is going to be almost always the most important thing. That's what we want to. That's what we care about. Usually, when you're running LiDAR, it's because you're going to be running topo. So what you care about is the ground. This is a fascinating one because this is what some of the automated classification routines pulled out. Here's your ground. These ones in orange are going to be buildings, which they're clearly not, to a human at least. Those are clearly in vegetation, blah, blah, blah. But also you gotta be aware there's still some gaps. So let's talk about actually identifying ground surface. And one of the weird questions that you have to ask with this is, what is ground? These automatic classification routines try and find a ground surface. And in many, 95% of circumstances, what is ground versus what is an object is pretty clear. But there are a lot of edge cases. I mean a lot of edge cases, starting with a debris pile. Say you had that big pile of concrete. Would you call that ground? It's kind of a judgment call, right? In some cases you do want it to be ground, in other cases, no, that's trash. You exclude that as debris and you get the surface underneath, but that's, rock and rubble. Maybe that's what you actually care about is calculating that surface or something like that. That's a judgment call and there's no right or wrong answer to it. Same thing with a stockpile. Is the stockpile itself ground, or is that going to be a separate object and you care about the ground underneath and then you measure the volume of the stockpile as its own different classification? Once again, that's a judgment call. It really depends on the type of survey that you're doing. Same thing with things like rock outcroppings that, is that an object or is that actually part of the ground? Now, imagine all of these were under trees and you couldn't actually see it whatsoever. All you can see is the LiDAR outline of something, and it's under trees and you see a hump. What is that? Is that ground? Is that a rock outcropping? Is it a debris pile that we should call a piece of the ground? Or is it a car that someone parked there and shouldn't be considered part of the ground and it's an object? These are the type of things that automatic classification routines have a really, really hard time just discerning between, because they don't actually see what it is. They don't have the context. Even the most advanced AIs in machine learning and point cloud methodology don't have the context to be able to know, oh yeah, clearly that's someone abandoned a car underneath the forest and that's what that is, so I'm going to exclude it as part of the ground. Those are hard judgment calls to make, and this is part of why a lot of these automated routines, they still require human judgment, and they still require a good amount of work to be able to identify what is ground. And this is just one class, right? This is just what is ground, what should be the simplest thing. But when you're not there on the ground, you can't see what's under the trees. You can only see the elevation data from the point cloud, and that does require some judgment of knowing the site conditions, what's there. Is it by a junkyard and there's a bunch of junk that you want to exclude? Or is it a, pretty much virgin land and you can say, okay, if there's something there, that's got to be a land feature. I don't know what it is, but I'm calling it ground. So all of that is pretty important. Automatic ground classification has a whole bunch of different inputs as well, as far as what your expected terrain slope is. What deviation from that terrain slope will you call ground versus non-ground? How awkward of a shape does it have to be before you say, that's definitely not ground, right? And then there are a lot of different filters in there, from what's your expected terrain slope, and then how long does it have to deviate from that slope for you to call it non-ground points anymore. Stockpiles are a particularly weird one because they show up as a cone, and that cone, whether it's ground, it's like a 45-degree angle of a stockpile cone. The software says that's way too steep to be natural ground, so it kind of excludes it. Because likewise, if you see a car oftentimes is not too dissimilar from, just a mound, and it sees that and says, oh, it's a car, that's definitely not ground. You and I can look at it and say, that's a car. The computers have a lot more trouble from an AI perspective or any sort of automatic classification routine of determining a car from a stockpile. One needs to be included, your stockpile does, your car needs to be excluded. That's a real challenge, and that's where tweaking everything to the right site conditions is important. This one is just an example of two different settings that you can have to allow for some steeper terrain. That one doesn't like a steeper terrain, that one does.
Same piece of software produced both of those, just with different
with different settings, and that's what it is. And there's no, like before, like photogrammetry, there's no magical setting that works on all sites. We spent a stupid amount of time trying to discover with our Lidar teams, we were doing this, what are the optimal settings? And it was a big, almost aha moment for us when we realized, well, duh, I teach this type of stuff. There isn't one set of settings. How did I not figure that out earlier? It's about finding the right settings and having these procedures to say, oh, okay, so we're working in a mountainous area of Hawaii. It was actually a Hawaiian project that I did in the middle of December and made me really depressed because I wanted to travel to Hawaii. But that made us realize this because it was this steep hill with a road running through it with all of these crazy jagged rock outcroppings that were natural ground, and we had this software settings that we thought were these magical settings, and it was taking all of this ground and throwing it out, saying, nope, that's way too sharp of a feature, that's not natural ground, it can't change like that, and it was causing all kinds of problems. And then we switch it the other way, and it's like, okay, so these really sharp features, that's ground, and so it would take these trees and say, all right, that tree is ground now, and we're like, context here. So it took a while to get those settings dialed in, and it was very, very different on that site than to something that is mostly flat with maybe only 5 or 10 feet of true ground elevation change and 100-foot trees. Those will have a way different set of parameters. So realizing, like Pix4D, like software, it's not about the settings, it's about the workflow. It's about the procedures, that's how you get it. There is no magic set of settings that we've found. There is no AI that is reliable about that. There is nothing that can see underneath the trees and say, that's a car, that's a stockpile. That counts, that doesn't. And sometimes you don't know for sure, and it takes a human judgment to mark it as unidentified object on a CAD template, right? Mark it and say, there's something here, I don't know what it is. That's oftentimes just as important. Grass, shrubs, low vegetation, those require some of their own parameters as well too. As I've mentioned, a point cloud is a cloud. It is not a perfect set of points. So being able to say, okay, here's your statistical average of what we see typically as a spread of about 1 foot on hardscape. That means anything over 1 foot, we are going to classify as grass, and that's what it looks like here. This would be a low vegetated area that all of this stuff would be called the ground, and all of this would be called the grass. Once again, trying to optimize that. And then buildings, power lines, all of that. Number one thing is ask yourself, is it worth the time? Automatic classification algorithms have a lot of false positives. We do start with automatic classification, but again, focus on ground. That's going to be the most important. All right, once again, I'm running out of time, so we'll go to the last step in Lidar processing now, which is creating raster data. So first off, what is raster data? Raster data is a matrix of cells or pixels organized into rows and columns. Basically, it's pixel data as opposed to vector data, which is going to be points and polylines typically. So why do I want, Lidar data is by itself vector data. Lidar data, or vector data is Lidar data, topo points, break lines, tin surfaces, contours, that sort of thing. Raster data is going to be your ortho photos and your DEMs and DSMs. So if we're starting with Lidar that's vector data and we want to get to a tin surface which is vector data, why would I input a step of creating it into raster data? And that is a valid question. And the answer is, it's not a necessary part of the Lidar workflow, but we have found that creating a step that creates raster data from your raw point cloud makes it much easier to work with, and it can help smooth out much of the noise from your individual points. So here's a great example of a surface with some light vegetation. Here's the raw classified point cloud. You have your ground point data, which is kind of noisy here. This is going to be your vegetation. This is going to be a profile of a surface. It actually could be, this one is of a highly precise tin surface where it's taking most of these points and making a tin out of it. And what you can see is it actually creates a lot of really jagged, ugly surfaces. Whereas if you rasterize it and actually have like a 1 foot bin size, what this one actually does is it effectively smooths it into 1 foot bins and takes the mean of all of the hundreds of points within each individual bin, it actually smooths it out. And our analysis after the fact has actually shown that this is a statistically more accurate surface than the noisy one is.
Interesting, that is exactly what we do with hydro data.
Is it really?
Yeah.
Yep. Doesn't surprise me at all, right? This is ultimately
validation for your process.
Well, thank you. So yeah, we find that rasterizing it and smoothing it and taking the average has statistically provided better results than trying to take a really precise, every single point being true, that sort of thing. As I've mentioned, point clouds are not a perfect set of points. They are a cloud, and taking the average makes it better. So the workflow that we use to go from a point cloud to an actual CAD tin, you start with your point cloud, creating a raster grid. Resolution and bin size, we typically like about 1 foot for each individual pixel. And with we find mean or median, depending on the individual sensor, both work. We don't like using minimum because of what I've said about them being clouds. Converting that then to individual points and polylines, using basically extracting topo points from that grid, simplifying it down in the Lidar or in the Linework drafting process, and potentially adding in break lines, things like this. You would have a break line, you would draw break lines along the creek bed and probably do a grid of points and maybe a low pass filter along some of the rest of this to get a topo points, get a tin surface out of that. Get those points and polylines to a tin surface and then add your contours to that. That is what our workflow typically looks like for actually going from the Lidar, the classified Lidar data into the tin surface and contours on the topo side of things. For Linework drafting, since we are running out of time, shoot me an email. I have talked about that in depth at other presentations as well, because the Linework drafting is the step of just going through and extracting the data that you need. These are your different softwares. It's tedious, like with other things. There are automation tools that help, but are not the magic bullet. And Linework drafting does take an awful lot of time. So again, shameless plug, this is the type of stuff that we do as a company. If you don't want to sit there and draw topo points and break lines for hours and hours in a row, we do. And then putting it all together into CAD, merging it, and getting your final survey deliverable. So once again, we are now wrapping up, and so I won't hold you guys away from the happy hour any longer. And once again, if you want a recording of this, then please sign up at LSAW22, aerotos.com/LSAW22, or you can shoot me an email with any questions you have. My email is logan@aerotos.com. So, thank you again on a Friday afternoon for the questions, the interaction, all of that. I truly appreciate it. I appreciate your attendance and sticking with me. Thank you.